All right, we'll continue on from here then. Classification according to side lengths. If it has no sides the same, it's called scaling. Okay? If it has two or more sides congruent, isosceles. Students get those two mixed up a lot. So you're gonna have to think how you remember which is which. And then what if all sides are the same length? Equilateral. So by that definition of isosceles, do you understand that an equilateral triangle is isosceles? Isosceles says at least two sides congruent, so if all three are congruent, it is an isosceles triangle. So it's like a subset of isosceles is equilateral. We're always going to use the most specific word, so if it has only two sides, it'll be isosceles. If it has all three, we'll use equilateral. All right, so what were some terms you didn't have? Right triangle, what are the legs, what are the hypotenuse? Right triangle has how many right angles? One. Okay. So here is my right angle. Which ones are the legs? They are the two sides that form the right angle. So if you didn't get that in your notes, the legs are the two segments that form the right angle. And then the other one that's across from the right angle, that's the hypotenuse. Students like to say, well, the hypotenuse is the longest one. Well, that is true. Sometimes it's hard to tell which one is the longest, so it's probably easier to discuss it in relation to the right angle. Yeah, I was going to say mark a right angle in your triangle there. And the hypotenuse is not always the slanted one. That's another way that students describe it to me. So I usually then draw the triangle like this. Here's the right angle. Which one's the hypotenuse? The longest side, I can't tell which is the longest. Tell me more.
The bottom one?
In this picture, the bottom one. That's the hypotenuse. This would be the leg, and that would be the leg. Now in your isosceles region there, that box, it has legs, and it's not hypotenuse, it's base. Okay? Now in an isosceles triangle, the legs are the two that are congruent. The legs are the two congruent sides. The other side is the base. Is the base always the bottom? No. Just depends how you turn it. Is the base always shorter? No. Depends how it's formed. So here's one. I'll draw more obtuse. Are these two sides the same? So this one is a leg. This one, leg. And then the one over here is the base. So whichever side is not congruent to the others is the base. Did that get all the terminology then? So, all right, I have just a few more sample type problems to do. This one's very similar to the bell ringer. So for some of your notes, find the side lengths of this triangle. How would you go about finding the actual side lengths? And notice we're doing sides, not angles. How long are the sides? So figure out a way to find x. I'm seeing x as 8.5. Okay. So x hopefully comes up right here. 8.5, and then substituting in, get that part? Substituting 23.3 and 23.3, and then 44.5. Didn't look like you struggled on that too bad. All right, how about another one? Now looking at the picture, there's no tick marks, so you better read the directions. What kind of a triangle is it? Well, what's it say? Got to get all three sides the same. So now substitute that number in. pretty sure it says y equals 7. If I can click it, I did things out of order a little bit there, it looks like. Okay, so y equals 7, and then when you substitute in, what were you telling me? 17 for each of them? Okay. How about a little story problem? A steel mill produces roof supports by welding pieces of steel beams into equilateral triangles. Each side of the triangle is 18 feet long. How many triangles can be formed from 420 feet of steel beam? I need to read again. It tells you what kind of triangle. It tells you some information about the measurements. What kind of triangle, Grant? Which means?
All sides are
Correct. How long are the sides? Zach?
18 feet.
So how much steel does it take to make one triangle? 54, and you're getting that by 18 plus 18 plus 18, or 18 times 3. Okay. All right, so 54 feet for one triangle. How many triangles can I get out of 420 feet? What do you need to do to figure that out? Yep, 420 divided by 54. 50 times 8 would be 400, so it's around 7, not 8. Does it round up to 8? 7 is how much? 380, so can you get an 8th one? Can you make an 8th one? No. So this is a type where even though it was maybe 0.7 repeating, you have to round down in this story because you don't have enough to make the 8th triangle. So think about the correct rounding. In real life situations, it doesn't always follow the rules. Okay, so make 7 triangles as possible. So some story problem about that type. And we did that already. Section 4.1, make sense? There will be a little bit homework based on this, on that section. Before I go to the next section, here's a little musical interlude here. James Blunt on Sesame Street. Someone want to catch the lights for me?
This right here.
It's outside the triangle.
They're also pointy.
They are pointy. And what else did you catch on?
It has a narrow top and a wide base. And they're colorful.
Very good. Even the hypotenuse.
The base is long too.
On that one. Yes. What kind of triangle was dancing? Well, how would you classify it?
I'd have to look at those, but I don't know because I was just not in the song.
Equiangular?
I thought it looked equiangular, equilateral, probably. The nice perfect triangle idea.
Ball my eyes out. That was
Ram.
a cute song.
Now I'm glad you were touched. All right, at least there was some reaction then. All right, some vocabulary things in section 2 for us. Okay, the first, making all 3 angles adjacent. They're all the same vertex. I'll take them down so that they stay flatter there. Okay, I don't know if I laid them correctly, but anyway. To show you 3 angles in the triangle, make a straight angle. How many degrees for a straight angle? 180 degrees. So all 3 angles of the triangle make a straight angle, so all 3 do total 180 degrees. There are other ways to prove it, but that's one way to kind of demonstrate that they add up to 180. So we're going to find some missing angles in normal numbers and then in some algebra terms. How would we really prove it? Because what I did up there is not really a proof. If we're going to prove it, we need what's called an auxiliary line. Is there a definition of auxiliary line on your sheet there? An auxiliary line is a line that you add to a diagram so that you can do a proof. Well, the auxiliary line that we would have to add to the triangle is this dashed one. And we would need to say that it's a parallel line to this side of the triangle. So we'd have to add that to the diagram. Now, how is that going to help us prove the 1, 2, and 3 add up to 180? Well, what did we just talk about for angles like 4, 2, and 5? On the board, we said that they make a straight angle. So wouldn't the measure of angle 4, 2, and 5 have to total 180? Straight angle total? Okay, now with that parallel line added to the diagram, angle 1 and angle 4 are congruent because of
The alternating interior angles.
theorem. Okay. So if angle 1 is congruent to angle 4, like we just said, alternate interior angle theorem, that means their measures are equal. So I'm going to take out measure of angle 4 and substitute measure of angle 1. Okay. Let's go to the other side. Angle 3. Angle 5. Alternate interior angles again. So since the lines are parallel, we have those two congruent, which means their measures are equal. So I'm going to substitute, instead of angle 5, let's put measure of angle 3. They're equal. I don't want to substitute for angle 2. I'll leave it. But notice by substituting, what have I just proven or demonstrated? That all 3 angles of the triangle have to add up to 180 degrees. So we had to add that auxiliary line as a parallel in order to do the alternate interior angle part of that explanation. So that's an actual proof of the theorem instead of just demonstrating it. Auxiliary line was added so that we could do the proof. All right, I think that's talking through it. Okay, so what I did was kind of wrote it more in a complete equation. But all 3 angles have to add up to 180. So I subtracted, actually I added those together and subtracted at the same time. What'd you say your final answer was? 78 degrees. So I used the triangle sum theorem, subtracted the 62 and the 40 to see what was left. All right, same diagram. But I want you to find angle YWZ, this angle now. So take a look at what you know in the, how are these two related?
Supplementary.
Supplementary because they form a linear pair. So we're thinking linear pair theorem. So supplements, what's 180 minus 62? 118 for that one. What should be 120? The angle answer? Or this one? I think 180 minus 62. Yeah, when you borrow. All right, so what can we do after we get that 118? Look at the skinny triangle.
118 plus 12 minus 1.
Okay, so the angle that we're looking for, can I call it just angle W? I believe I can. Okay, angle W, 12 and 118 has to total 180. All 3 angles in that skinny triangle. These two total
130.
130. So did you say take 180 and subtract 130? Okay. So after all that, we get measure of angle W to be 50 degrees. What are the theorems we used? What theorems did we use when we went through that? We did linear pair theorem. That gave us the supplements. We used the supplement definition to know what that meant. What else did we use? The triangle sum theorem. That was where we got it totaling 180. That was our triangle sum theorem. Anyone think through that a different way that you want to discuss? Okay, let's go to the next one then. How about y, let's see, I guess that's still continuing the one that we just did. All right, I know this picture is a little bit harder to see, but it's put on a map. We're supposed to find the measure of angle MJK. If this is 48 and 88, that adds up to 136. Subtract from 180. How much? 44? So that's what this red arc is, 44 degrees. How can that help me? This other red arc is 44 degrees, not the double one that I drew in. But now the triangle that has what we're looking for has 104 degrees and 44 degrees. You're missing one angle. So 104 and 44 add up to 148. 180 minus 148 is 32. And that's the angle that we're looking for, 32. Could we do anything on this triangle? At first I thought no, but yes we can. Morgan, put your iPad over on the shelf over there, please. Okay, what is this missing angle? Because these three have to add up to 180. So is that 32 also?
Yeah.
Got the same numbers as last time, right?
And the last one is 78.
78, did he add right? 102. Okay. So we found more than what we needed to. Are there parallel lines in this diagram? Kelsey's saying yes. Do you have support? Because I don't see any arrow markings. Is there support that there are parallels? There is. Anthony? There. Okay, converse of alternate interior angles. So like these two, knowing that they were congruent, converse of alternate interior angles would prove then that these lines would have to be parallel. And our 32s kind of approved or supported that also. So there are parallels that we can come up with. They weren't there. And in our thinking, we really didn't need them. All right, how about this one? Got a diagram. It's a very simple kind of map. John's house, Kay's house, the store. What's the angle the two houses make with the store? So I want you to figure out this angle. What's the store's angle? What kind of equation? Name the theorem. Okay, arrived at an answer? Yes, no, yeah? Okay, you added them all together, right? Set it equal to 180. I got y to be 12. So then the angle was 30 degrees. Okay, thumbs up or down? I'm not seeing enough response on this side of the room. That side of the room's got responses over here. Okay. Okay, question on that one? Triangle sum theorem, all the angles have to add up to 180 inside the triangle. Well, what if it's a right triangle and one angle's 90? What could you tell me about that triangle then, or the rest of the angles? One angle's 90, what do the other two have to total? 90. What are two angles called that add up to 90? Complementary angles. That idea is called the, okay, that is a corollary to the triangle sum theorem. There are two corollaries. Now what is a corollary? A corollary is a theorem, but it's a theorem that doesn't have a major idea by itself, you can come up with the proof of this theorem by using another theorem. So that's talking through just a little bit ago where the triangle sum is 180. If one angle's 90. Anyone still need the screen? Okay, so here's an example that you can use one of those corollaries, step work, I guess. So we're applying that acute angle, or what was it called, right triangle corollary. The two acute angles in the right triangle have to add up to 90. If 163, when you subtract, you get 27. Oh, that was kind of tough getting there. One of the acute angles in a right triangle measures 2x. So now I just threw it in as a variable. What's the measure of the other? I still think you need to say it better. He's saying the acute angles are 90 degrees. Add up to 90 degrees is what we need to throw in there. Okay, so the angle that you're after, so we just say measure of angle A. The measure of the angle I'm looking for and 2x have to total 90. So how would I get measure of angle A? Well, subtract 2x. Measure of angle A is 90 minus 2x. Can you come up with a way to combine those? No, they're not like terms. So that one, when they throw the variable in, you're just going to have an expression like that. Does that make sense once you see it? Okay. And Morgan, you were saying 180, I think, instead of the 90. So get that straight in your head. Okay. All right, and I didn't make a problem with the 60s because that's too easy. If you flip the page, we have a little bit to finish about exterior angles. On triangles, there's an interior and there's an exterior. The interior of the triangle is the inside part. The exterior is the outside, just like you would assume the words would mean. So we have interior angles and exterior angles. The interior angles are just the 1, 2, and 3 that we were working with. And look to see how the exterior angle is formed. It's formed by one side of the triangle and an extension of an adjacent side. So it's formed by this side of the triangle, and this is an extension of one side. So if I extend that on out, it makes angle 4 on the outside of the triangle. You could extend up this way if you wanted to. That makes another exterior angle. I could extend this way. What if I extended back this direction? Well, that does make another exterior angle. Is the one up here an exterior angle? No, because it's not formed by one side of the triangle and an extension. It's formed by two extensions. So there could be, didn't do that very well. There could be an exterior angle at every corner. There actually could be 2 of them. Exterior angle, you have to extend a side. So don't just randomly draw it out. You have to extend a side. So the exterior angle, we're going to have a theorem in just a little bit. And I need to make sure you understand what a remote interior angle is. All of the angles 1, 2, and 3 are interior. A remote interior angle is an interior angle that's not adjacent to the exterior. So 4 is my exterior angle, 3 is adjacent to it. So the remote interior angles are 1 and 2. Let me go to the board here and draw you a little different picture. Let's go this way. 5, 6, 7, 9. Okay, the exterior angle is, which one's the exterior angle? Angle 9. Which ones are the remote interior angles? Interior angles that are not adjacent to it. That would be 7 and 5. These are the remote interior angles with that exterior. Let me put a different one up here. Let's extend this way. 4. For angle 4, which ones are the remote interior angles? Interior, but not right beside it. Okay, 6 and 5, this one and this one, not angle 7. Why is it important that you pick out the remote interior angles? Well, because of this theorem. It's called the exterior angle theorem. Let's put some numbers up there and see if this really does work, what it says. And maybe think of why it works that way. Okay, let's make a problem. Angle 2, or angle 1, let's make that 40 degrees. Angle 2, what's that look like? 70 degrees? No, maybe not 70. Maybe 80. Looks more bigger than that. Okay. Now the theorem says that angle 4 is going to be how many degrees? The exterior angle is the sum of the two remote interior angles.
Equal what they are equal to.
So it's what those add up to be. So,
Should be 120.
okay, so it's, the theorem says that angle 4 is going to be 120. Well, let's see if we can get there. What's angle 3?
60.
Now, how are you coming up with that 60?
Subtract 80 from 180 and then subtract 40 from that.
So the theorem you're using is triangle sum theorem. Okay, so he's doing triangle sum theorem, and he's figuring out that the measure of angle 3 ended up 60 degrees. Now, if angle 3 is correctly 60 degrees, angle 4 is a linear pair with angle 3. So angle 4 would be 180 minus 60, 120. And that's what the theorem said it was going to be, 120. But why does that work? Will it always work? Well, instead of specific numbers, let's just think in general. When we were putting it together, didn't we make angles 1, 2, and 3 total 180 degrees? And Kiernan gave us the reason. Why? What was the reason that angles 1, 2, and 3 had to total 180? Vanessa? Triangle sum theorem. Okay, and as we were working through, I think at one point we used the fact that 3 and 4 were supplements. They had to add up to 180. What was the reason behind those two being supplements? Think back. Wasn't new today. That was the linear pair theorem, right? Okay, so remember when we did a substitution? I'm going to write this first one down, but I'm going to take out 180 degrees and put something else in its place. So measure of angle 1 plus 2 plus 3 equals 3 plus 4 is the same as 180. So I can substitute that. Well, why would I want to do that? I'm going to subtract measure of angle 3, the same thing from each side. And so what I get, measure of angle 1 plus 2, those two remote interior angles will always add to be the exterior angle. I don't have all the reasons written up here, but I said them. Okay? So you can prove that this theorem does work. Let's see if you can use it. Can you find measure of angle B? The exterior angle is the sum of, so we subtract angle B is 108. Okay. Exterior angle sum was, or exterior angle theorem was used. How about this one? Doesn't just have the degree measures. Now we're going to have to write more of an equation. Okay, so write down the exterior angle, 5x minus 60. has to equal what plus what? Divided by 3, is that what we're doing? X is 26. So then how do I find angle B? 2 times 26 plus 3. 55 degrees? Does that one make sense? The theorem that we're practicing in that one is exterior angle theorem. If I put variables in, you have to know the theorem, otherwise you can kind of get by without it. Okay, and there's one more theorem, right?
Yeah.
Third angles theorem. So let's zip to that one. I'll skip over this example. That one just had a right triangle in there. Okay, the third angles theorem, if two angles of one, why does that work out? Should we try it with some numbers? L looks like our 80 degree, so we'll make R 80 degrees also. S is kind of small, we go 30. And M is also 30. So if those two angles are the same in the triangles, what's the last angle in the first triangle? What's angle N? Triangle sum theorem, what do they have to add up to be? There's no exterior angle here, just they have to total 180. And this is 110, so 70 degrees for that angle. And the other triangle, same two angles, same 110 total, so the last angle ends up being 70 also. So why are those last angles the same, Morgan? And you're going to get the same total for the starting angles in both triangles, right? So then that last one when you subtract will always be the same. Sometimes this one is a hard one to pick out, but realize there's two triangles. You've got to have two angles in one triangle and two angles in the other marked the same. We actually use this one quite a bit through our course. Third angles theorem. 2x squared has to equal 4x squared minus 32. Now that has a squared in there, so let's look at the solving. Okay, subtract 4x squared from each side, divide by -2, and square root. You really don't have to square root because you're going to substitute x squared back in. So they kind of skip that step in the solving.